Hello everyone, today we will discuss the variational principle. This principle is useful in the advanced formulation in quantum mechanics and electrodynamics. Here we will find the Euler-Lagrangian condition by using the variational principle. For the calculus of variation, let us suppose there is a function fy y dot x where y is equal to yx between x1 and x2 points and y dot is equal to dy upon dx. Here the problem is that we have to find a curve y is equal to yx such that the integral fy y dot x dx has a stationary or optimum value relative to paths which are small differ from the correct function. Now here in this diagram you can see that let us suppose that this is the initial point of your home and this is the end point of your home, and you are reaching from point A to point B through two different paths. And let us suppose that the red path is the correct path and there is the other path which is the green path. It is slight different from the correct path, and let us say it is represented by yx alpha and the correct path is represented by yx0. Here alpha is a parameter. So here you can see that at the end points which is the A point and B point of your home, these points are fixed, so there is no variation at these points can be found. That means the difference for the two curves at the end points will be 0. So yx alpha minus yx0 at x equal to x1 will be equal to 0, and let us say it is equation number 1. Then yx alpha minus yx0 at x equal to x2 will be equal to 0. Let us say it is equation number 2. Let us denote the line integral for the yx alpha curve as I alpha is equal to x1 to x2 fy y dot x dx. Let us say it is equation number 3. Here f is function of y dot and x. Because y is function of x alpha, so we can write it as I alpha is equal to x1 to x2 fy x alpha y dot x alpha and x dx. Let us say it is equation number 4. Now if there is a slight variation in the second path, then we can write del I over del alpha as x1 to x2 del f over del y over del alpha, then plus del f over del y dot over del alpha. Because x is not a function of alpha, so it will be del x over del alpha will be here 0, so this term will not be written here. So here del I over del alpha is equal to x1 to x2 del f over del y over del alpha plus del f over del y dot over del alpha into dx. Let us say it is equation number 5. Now here we can define the green curve as yx alpha is equal to the correct path yx0 plus alpha eta x. Here eta x is the function of x and alpha is a parameter. Let us say it is equation number 6. So if we find here del y over del alpha from this equation number 6, then we can write it as del y over del alpha will be equal to eta x, then del y dot over del alpha will be equal to eta dot x. Let us say it is equation number 7. Now we can write del I over del alpha as x1 to x2 del f over del y del y over del alpha plus del f over del y dot over del alpha into dx. Let us say it is equation number 8. Now if we integrate this term by parts method, then we can have first as it is the integration of the second, so it will be del y over del alpha, then the limits are used here, x1 to x2 minus whole integration, the differentiation of the first, so it will be d over dx del f over del y dot, and integration of the second, so it will be del y over del alpha, then whole integration. Now see here, del f over del y dot del y over del alpha, this term is equal to eta x, and at the end points it vanishes, so this term will be equal to 0. So we will have from this term only this value. So in place of this term we will write this value, so we can have the integration x1 to x2 del f over del y and del y over del alpha minus d over dx del f over del y dot and del y over del alpha into dx. Let us say it is equation number 9. Now our del I over del alpha will be written as x1 to x2 del f over del y minus d over dx del f over del y dot, then we can take common here del y over del alpha, so it will be taken as out del y over del alpha into dx. Let us say it is equation number 10. Now we can write del y over del alpha as equal to eta x, so del I over del alpha here will be equal to x1 to x2 del f over del y minus d over dx del f over del y dot eta x into dx. Let us say it is equation number 11. Now as we have assumed that we have to find the integration that it remains the stationary or optimum value, so we can write del I over del alpha is equal to 0. Now when your del I over del alpha is equal to 0, for maxima or minima you know that dy over dx is equal to 0. Similarly here for stationary value del I over del alpha is equal to 0. So here your term x1 to x2 integration del f over del y minus d over dx del f over del y dot eta x dx is equal to 0. You know that at the end points eta x will be vanished, so we will take only when we use the limits this term del f over del y minus d over dx del f over del y dot, and this term will be equal to 0. So this is called as the Euler-Lagrangian condition, del f over del y minus d over dx del f over del y dot equal to 0. Thank you.